Okay, so you can see maybe it's probably going to be small, but you know, write it down. You should have written it down. Look at the previous video if you didn't. Okay, there we go. Maybe you can see the equation that we're studying. Well, this is the solution to the differential equation. Only before I had a square root of lambda, and sorry, stupid phone. Before a was the square root of lambda. I just have a now, so a is equal to the square root of lambda. This is the solution here. And so a is equal to 0, so we're dividing by 0 there, so this is not defined. But if I increase a little bit, I start getting the type of functions that I want to see here. So I'm going to increasing this. Hold on a second. Let me go back to 10, and let me do 0.1 here. Okay, so we can see here. This is the solution here, and when we have 0 here, I'm going to call this phi of x. When phi of x is equal to 0, that means a is going to be a new eigenvalue, or rather, a is equal to the square root of the eigenvalue, so a squared is going to be the eigenvalue. So we see what happens here. It looks like around 0.1, maybe even a little bit less if I, let's say, go by 0.01. It's going to be a small step size there. Let's see if I can try to figure out. Okay, so 0.07, somewhere around there. Maybe if I do 0.05, 0.01 or something, we're going to figure out what the first eigenvalue is. I'll let you figure that part out. And then we see what happens. I'm going to go back to step sizes of 1 here. Sorry, not 1, 0.1. Okay, so I'm going to zoom out here. And now what's going to happen if we increase if we increase a, so we get more and more and more. So now I just want to point out a couple of things. Right around here, we get our first eigenfunction. And notice that should be exactly 0 at 1 if it was the actual eigenfunction. So here we are at the first eigenfunction, so k corresponds to 1 in the Sturm-Liouville theory. And k minus 1 is 0. It says there are 0 zeros in the interior of the interval from 0 to 1, and that's exactly what we have here. So we're going to increase it, and we see what happens here. It increases this way, this way, this way, then it's going to start to curve back down again. It's going to come back down. Okay, so now here at about 4.5, so the square of that is going to be our next eigenvalue. And notice this is the second eigenfunction. The second eigenfunction, according to the theory, should have exactly 1, 0 in the interior of the interval. That's what we have here. And if we increase more and more and more, we can see what we're going to get up to 1. Okay, I'm skipping over it here. I don't know, somewhere between 7.7 and 7.8. If you do the square of 7.7 and the square of 7.8, somewhere in there is going to be the third eigenvalue. And so this is going to be approximately equal to the third eigenfunction. And again, we've got 2 eigenvalues in the interior of the interval. Okay, now this is one way we can do to try to numerically find the eigenvalues. Now, if you want to make like a computer program do this, there's a couple of things that you can do. Using theory that we're not going to get into, if you know information about the boundary conditions, about the P, about the Q, and about the sigma, you can get sort of asymptotic expansions or asymptotic approximations for the locations of the eigenvalues. And so, for example, you could do a Newton's method and use those starting values. So you could use some sort of Newton's method and use those approximate locations as the starting values for Newton's method, or you could use something like a binary search method and use those as starting values for to get an interval for a binary search method. If you want to know more about that, ask in the discussion forums, and I can give some thoughts. Another thing that we can do is we want to take this equation, make x equal 1 and set that equal to 0. So we did that before. So I'm going to get rid of both of these. And so that gave us tangent of the square root of lambda equals the square root of lambda. And here we're going to look at positive. So I'm going to graph x, and this is going to be for x greater than 0. And I'm going to, and I'm going to graph tangent x, and this is going to be for x greater than 0. Okay, and where these two curves intersect, that's going to give me an eigenvalue, or the square root of an eigenvalue. So this again is x is kind of the stand-in for square root of lambda. So we want to think about this as tangent of the square root of lambda is equal to the square root of lambda. And so x then is equal to the square root of the eigenvalues. So if I look at here, no, actually down around here is where the first intersection is going to happen. It's going to be very difficult to figure that out. But if I look at the next intersection point, it's going to be right around here. That's going to correspond to 4.493, where that intersection happens there. So the square of that is going to be the next eigenvalue. That's 7.725, that which is, corresponds to what we saw before as well. That's going to be the next eigenvalue, so on and so forth. And if you want to do it directly, I could do square root of x here, and then here I could have square root of x. And that's also going to give me, wait, why is that giving me a problem? Oh, like this. Okay, and so again, this intersection is the exact, 20.190, that is the eigenvalue. You don't have to square it to get the eigenvalue. There's something that I wanted to point out in the previous thing that I was looking at that I didn't point out. So we're going to go back to minus cosine of ax plus 1 over a sine of ax. I'm going to add a slider here. I want to start it at 0, go up to 10.1, and then 0 less than x less than 1. So we talked about the boundary condition at 1. I want to show that the boundary condition at minus 1 is satisfied, or sorry, at 0 is satisfied. So if you remember, the boundary condition is phi of 0 plus phi prime of 0 is equal to 0. So phi of 0 plus phi prime of 0 is equal to 0. Now we can see here, no matter how I change my a, the condition here is not changing, right? If I go up, if I go down, whatever, phi of 0 is always equal to minus 1, which might seem like there is an issue because we need phi of 0 plus phi prime of 0 to be equal to 1. And as I change, it seems like maybe the derivative is changing as well. But actually, if we zoom in enough, like if we zoom in a very, very, very long ways, I'm going to zoom in all of this way here. I might even need to zoom in a little bit more, but I'm just going to keep going. We notice that as I change this, as I change a, even if I go all the way up to 100 here, as I change a, it looks like the derivative is not changing at all. In fact, it really looks like the derivative, if I zoom in even more, the derivative stays at 1 this entire thing. So for example, if we graph y equals x minus 1, we're going to get this blue line here. I'm going to make it, whoops. I'm going to make it a dotted line like this, or no, maybe a dashed line under like this, and you can see the black line underneath it. As I move a, you see that the black line doesn't move away from the blue line. In other words, what it says is that the derivative here is always going to be equal to 1. At least that is what this graph depicts or gives evidence of, is that no matter how we change this, phi of 0 is always minus 1, and phi prime of 0 is always 1. Well, of course, this makes sense because we decided to pick phi prime of 0 equal to 1. That was how we sort of picked our parameter b. At any rate, I just wanted to illustrate that. Okay, so that's it for this video. These are two different numerical ways where we can determine what the eigenvalues are numerically.